Hello guys, welcome to this new video. Today we're going to talk about exponential and logarithmic functions. That's unit 9, and specifically we'll be talking about exponential functions. Okay. Before starting with that, I'd like to do a very quick review of the previous unit. Okay? Sequences and series. As you already know, I hope, we have linear functions. We learned linear functions previously this year. And a linear function, it's something like this. Y equals x plus 1, or f of x equals x plus 1, and this is like this. And then in this previous unit, we learned about arithmetic sequences or arithmetic progressions. An arithmetic sequence is the same thing or very similar. It's very similar to a linear equation, but the difference is that it's discrete. Okay, so this is going to be the point 1, 2, the point 2, 3, sorry, 2, 3, sorry. Okay. The point 2, 3, the point 3, 4. Okay, so this red line is a linear equation, a linear function. It uses x, which is the continuous variable. We have values at every single point here, and these points are representing an arithmetic sequence that, as you know, instead of using the continuous variable x, we use the discrete variable n. Okay, so it would be, instead of the first case, we have f of x equals x plus 1. That's a linear function. And we have an equivalent arithmetic sequence, which is going to be this. A sub n equals 1 plus n minus 1 times 1. I don't really need to write this times 1, but it's just to use the general formula. So as you already know, that red line represents the linear function, and those points represent the arithmetic sequence. But there's an equivalence, okay? So this is using the linear function is using the continuous variable x, and the arithmetic sequence is using the discrete variable n, which only takes values on the integers, on the whole numbers. Then, then we learned about geometric sequences. In a geometric sequence, as you already know, we have the point 1, 2, like on the first day, or let's, yeah, on the first day, we have 2 people infected with this illness or this disease, and then on the second day, they have infected 2 people each, and then on the third day, there is, sorry, on the third day, there are 8 people infected, and so on. Then on the fourth day, we have 16 people infected, and so on. Okay, as you know, that is a geometric sequence. Okay, then we have a geometric sequence here. Let's do it like this. A geometric sequence here, and as you know, insert equation a sub n is going to be, in this case, it's 2 times 2 raised to the power of n minus 1. So at this point it is 2, then it's 4, 8, 16. Okay, this is a geometric sequence, and now, as you know, this one is using the discrete variable n, discrete variable n, and there is an equivalence, or there needs to be an equivalence here, which is the exponential function. Okay, I'm gonna try to do it same as on top. So the exponential function, the exponential function is the equivalent to the geometric sequence, but using the continuous variable x. So in this case, the way we write this as a as an exponential function is like that. So in this case, instead of using the discrete variable n, we are using the continuous variable x. So I'm trying to leave it the same way as on top. So this is going to be 2 raised to the power of x. Okay, so it's like that. So this is the review. We learned linear functions, and now we know an equivalent way of expressing them with the discrete variable. We learned geometric sequences, and now we're about to learn another way to express the same concept, but with the continuous variable. Okay, that's the correspondence. So, starting with exponential functions, actually, if you think about the example, like the one I used for for explaining the geometric sequences, let me check if I still have this. No, I think I don't have it. Yeah, it's here. This drawing about the coronavirus spread, if you think about it, actually, it's a bit, this example is a bit not that much, not that realistic, okay? Because we are assuming here that, sorry, we assume here that these two guys, okay, they are going to infect two people each, but we are assuming here that these two infections are happening at the same exact time that then these two are happening, and these two are happening at the same time, and these two infections. In reality, as you might guess, it doesn't happen like that. Okay, geometric sequences are very, very useful for many advanced mathematic concepts or topics, but in real life math, in statistics and all of that, it's much more common to see things modeled with exponential functions. Okay, because actually, in this specific case, if you think about it, it's like between day one and day two, there might be infections. Okay, people are not waiting until tomorrow at 10 a.m. to make the infection. The virus is not waiting for a specific time to make the infection. Okay, so in real life situations, we use much more functions with the continuous variable x. That's why. So this could be an example of that. In your book, I'm reading in page 530, it uses an example that it's saying that the number of internet users worldwide since year, like since year two, since year 2000, the number of internet users worldwide has been increasing at a rate of approximately 17% per year. Okay? Since year, sorry, since the year 2000, the number of internet users worldwide has been increasing at a rate of approximately 17% per year. Okay, then let's write an equation to model that. And then we will talk about the properties of the exponential function and all of that. So let's model this situation. F of x, we have the original, according to your book, the original number of users was 400 million, or the number of users in 2000. 400 million. Okay. So let's model this situation. This is 400, original, that's my original number of users. And now insert, and now it has been increasing by a rate of 17%. As you might know from statistics, if I want to increase a quantity by 17%, it's just multiplying it by 1.17. And this is per year, okay? So I have to raise this to the power of x. Okay, let's draw that. Let's clear this. And I'm going to draw it, but I'm going to draw it the way I would do it in class. Okay, so the way I would do it in class is I would give some values, and I would use f of 0, for example. In this case, this is going to be 1, so this is going to be 400. Let's make this a little bit more clear. This is 1.17 raised to the power of 0. All of this becomes 1. So this is a 1. And this gives us the point 1, 400. Sorry, the point 0, 400. And let's change the configuration, the settings of the axis. That's there. Okay, the point 0, 400. So if we give it another value here, let's make f1. This is going to be 400 times 1.17 raised to the power of 1, which is the same as not writing anything here. So this is going to be 400 times 1.17. So that's 417. 68. So this gives us the point 1,468. Okay. Okay. Let's take another value here. This is going to be f of 5. Okay, very simple. 400 times 1.17 raised to the fifth power. So in this case, we have 1.17 raised to the fifth power. Okay, and that value I'm going to multiply directly by 400 instead of copying everything. So let's approximate this to 876,98. Okay, actually, we're going to approximate it to 877. Okay, now just we could draw the line right here. Okay, so let's just draw the function. Why am I doing all of this? Because I'm expecting you guys to do it in your notebook. Of course, GeoGebra is a very useful tool for you to check your results, but for the exercises, all the assignments and everything, you have to draw that in your book. So you need to know how to do this in your notebook. Then this is going to be, as you already guessed, 400. The way we write it is 400 times 1.17 raised to the power of x. Okay, and as you might see, this follows those points and it goes up. Of course, this means that at some point here, yeah, this is after 1 year, this is year 2000, here's 2001, and so on. But here in the middle, there are values, of course, like people, like the amount of users of internet users is not growing like a step. No, it's growing progressively. Of course, this is not going to be perfectly following that curve, but we are modeling real life situations using math. Okay, so a math model is not exact, it's an approximation, but it helps us to build formulas and to build predictions, to make predictions and everything. Okay. I'm gonna get here and I'll continue in the next video.